Everyone says the edge of our solar system is a border. Voyager 2 is proving it is more like a wound. The deeper scientists look at its deep space readings, the more that wound seems open, hot, and leaking. And right now, one old machine is still drifting through it. If you want the space stories that get darker when the real numbers come in, subscribe now and stay with me, because this one only gets stranger the closer you look. Voyager 2 began its trip on August 20th, 1977. It left Earth during the Cold War, when home computers were rare and most people had never even seen the outer planets up close. NASA built it to do something huge, but still limited. Race past the giant planets, collect images and measurements, and keep going until age finally shut it down. No one thought that nearly 50 years later, people would still be staring at its data and wondering if our own corner of space is less safe, less simple, and less understood than we believed. The spacecraft itself is not magical. It is about the size of a small car, with old electronics, a dish antenna, long booms holding instruments, and power from radioactive material that slowly fades year after year. But it did something no other spacecraft has ever done. Voyager 2 is still the only human machine to visit Jupiter, Saturn, Uranus, and Neptune at close range, and that alone would have made it one of the greatest missions in history. At Jupiter, it saw storms bigger than Earth and helped reveal a more violent planet than many expected. At Saturn, it studied rings and moons in detail. At Uranus, it found new moons and rings, then reached Neptune and saw the Great Dark Spot, a huge storm system in the blue distance. By the late 1980s, Voyager 2 had already done more than enough to earn a permanent place in science books. But the most unsettling part of its story did not happen near a planet. It happened much farther out, where the sun's influence stops looking like light and starts looking like pressure. That is because the sun does not only shine, it also blows. The sun sends a stream of charged particles outward in every direction. That stream is called the solar wind. A charged particle is just a tiny piece of matter that carries electric charge. But when billions of them flow outward all the time, they create a giant bubble around the solar system. That bubble is called the heliosphere, and for a long time it sounded simple enough to imagine, our star making a protective shell in the dark between the stars. That shell matters more than most people realize. The space between stars is not empty peace. It contains cosmic rays, which are very fast, high-energy particles from violent events like exploding stars.
Data from the Voyager mission helped show that the heliosphere blocks more than 70% of that radiation from reaching the inner solar system, which means our star is not only warming Earth, but also helping shield it. So scientists wanted to know where that shield ends. They called the outer border the Heliopause. The basic idea sounded clear. Inside that border, the sun's particles dominate. Outside it, interstellar space, meaning the space between stars, takes over. Before the Voyagers reached that frontier, many scientists expected the heliopause to act like a moving skin. The sun goes through an activity cycle that lasts about 11 years. During active years, it throws more energy and more chaos into space. So it made sense to think that the heliosphere would swell and shrink like a lung, breathing outward and inward as the sun changed. Then Voyager 1 crossed that border first in 2012. That crossing already caused debate because some of the signs looked right and some looked oddly mixed. Still, many researchers hoped Voyager 2 would clear things up. It was approaching the same frontier from a different direction, and a second crossing is often what turns a strange clue into a clean answer. What happened instead was the opposite. Voyager 2 did not solve the mystery. It made it harder to ignore. When NASA and other researchers went back through the deep space data in detail, the results suggested that the edge of our solar system is not a neat wall at all. Voyager 2 crossed the heliopause on November 5, 2018. At that moment, it was about 119 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, so that means Voyager 2 crossed at about 119 times that distance, or roughly 11 billion miles away. It was far beyond Pluto. In a region where sunlight is weak, time feels stretched, and messages take nearly a day to go one way. NASA announced the crossing on December 10, 2018, after the evidence had been checked. At first, the story seemed simple. Particles from the Sun dropped sharply, and cosmic rays from outside the heliosphere jumped and stayed high. Those were the signs scientists expected when a spacecraft finally moved from the Sun's bubble into interstellar space. But then the finer details started to bite. Scientists had expected Voyager 2 to cross at a noticeably different distance than Voyager 1. The two spacecraft reached the boundary at different times in the Sun's 11-year cycle and from different directions. If the heliosphere really expanded and shrank as much as many models suggested, those distances should have been more different than they were. Instead, the two crossing distances were surprisingly close. That may sound like a tiny detail, but it landed hard. It meant the border of the Sun's bubble was not responding in the simple way many people expected. Either the heliosphere was more controlled by outside pressure than thought, or its shape was more complicated, or the whole system was behaving in ways the clean models were missing. That was only the start. Now comes the part that turned a boundary into a warning sign. Voyager 2 carried instruments that could study plasma. Plasma is gas so energized that its atoms lose electrons, and both the heliosphere and interstellar space are full of it. Scientists expected the plasma inside the heliosphere to be hotter and thinner, and the plasma outside to be colder and denser. Voyager 2 did confirm that the plasma beyond the heliopause was denser. But just before the crossing, it found a broad, troubled zone about 1.5 astronomical units wide. In that zone, the plasma slowed, heated up, and became about twice as dense as the usual plasma deeper inside the heliosphere. So the border was not a clean line from the start. It was a disturbed region, almost like a pressure front building before a storm. And even closer to the crossing, Voyager 2 detected an inner layer beginning about 0.06 astronomical units inside the heliopause. That sounds tiny, but on this scale it was enough to show that the edge had layers, not a simple surface. Inside that narrow layer, plasma speed dropped while density and magnetic field strength increased. That means Voyager 2 was not just moving toward an outside region, it was passing through a stacked set of warning signs, each suggesting compression, strain, and interaction. The shield around our solar system was not ending neatly. It was being squeezed, bent, and disturbed. And then came one of the strangest details of all. After traveling for years toward this frontier, Voyager 2 seems to have gone through the final transition in less than one day. Think about that. A boundary region could stretch across huge distances, yet the last step from the Sun space into interstellar space happened in under 24 hours. That made the heliopause look both wide and razor-thin at the same time. It had a long approach filled with trouble, but the final break was sudden. If you were trying to describe a stable wall, that is not the pattern you would hope to see. It sounds more like a cracked dam, where pressure builds over a broad area, but release happens at one tight point. Part of the reason this reexamination hit so hard is that Voyager 2 crossed the heliopause in the southern hemisphere of the heliosphere, while Voyager 1 crossed in the north. Scientists did not just get the same experiment twice, they got two passes through two different parts of the shield. If both crossings had behaved in clear but different ways, the models could have been adjusted and the mystery would have narrowed. Instead, the two spacecraft agreed on strange points and disagreed on others. Both suggested the boundary was more complex than expected. Both hinted that the magnetic field outside was not making the directional turn people had predicted. But Voyager 2 also showed that the local structure of the heliopause can depend strongly on where you cross it, which makes the whole shield feel less like a smooth ball and more like a dented surface under pressure. That matters because models are supposed to turn limited data into a bigger map. When the map says the shield should breathe one way, but the actual crossings show something rougher, hotter, and more uneven, confidence drops. Researchers then have to ask whether the error is in the assumed shape, the outside pressure, the strength of the solar wind, the role of magnetic fields, or some combination of all of them. The more moving parts there are, the harder it becomes to predict conditions for the next generation of deep space missions. Another detail made scientists stop and look again. Voyager 2's plasma instrument could directly measure the speed, density, temperature, and pressure of the surrounding plasma. Voyager 1 could not do that in the same way after its own plasma instrument stopped working long before the crossing. So Voyager 2 was not a second witness. It was the better equipped witness for this frontier, which is one reason its readings carried so much weight. That direct plasma view gave researchers something priceless. They could watch the solar wind slow toward zero near the boundary. They could estimate how the conditions changed. Instead of inferring the border from only indirect signs, they could catch the border acting on the material around it. That is why the unusual heat outside and the broad compressed region inside were taken so seriously. And there is a human side to this too. Space scientists had spent decades building ideas about the heliosphere from theory, distant measurements, and a small number of spacecraft. Voyager 2 did not just add a data point, it challenged a mental picture many people had worked with for years. That kind of change does not happen because of one number. It happens when several careful measurements quietly point in the same uncomfortable direction. Have you ever trusted a map until one road proved the whole thing wrong? That is what Voyager 2 did out there. If that kind of science story is your favorite, like the video, subscribe, and tell me the moment this started feeling real to you. There is one more reason the results keep spreading through space research. The heliosphere is our nearest example of an astrosphere, which is just the name for the bubble a star makes around itself. If our own star's bubble is more complicated than expected, then other stars may also build shields with weak sides, hot boundaries, and shifting leaks. So Voyager 2 is not only telling us about home, it is helping scientists think about what the space weather around other planetary systems might be like too. And here is where the story gets genuinely alarming. Scientists had expected the nearby interstellar medium, meaning the stuff between stars in our local region, to have a temperature around 15,000 to 30,000 Kelvin. Voyager 2 found something more like 30,000 to 50,000 Kelvin near the Heliopause. In simple terms, the plasma just outside the sun's bubble was more energetic than many models predicted. That does not mean the region would feel hot the way a stove feels hot. Space there is still incredibly empty. But temperature in physics also means particle energy, and those particles were carrying more energy than expected. Something in that nearby interstellar region was stirring, compressing, or heating the plasma more than scientists had guessed. Why does that matter? Because a hotter outside pushes harder. If the medium around the heliosphere has more energy and pressure than expected, then the shape of the heliosphere, the strength of its boundary, and the way it blocks cosmic radiation may all be more uncertain than older models suggested. A weird temperature is not just a weird number, it changes the whole story of the shield. And the surprises did not stop there. Another analysis found that plasma density jumped by about a factor of 20 across the heliopause. That means the material outside was about 20 times denser than the plasma just inside the boundary. That strong jump confirmed that Voyager 2 had really crossed into a different region, but it also showed how abrupt and extreme the transition could be. If you were expecting a smooth handoff from one environment to another, this was not it. The border looked compressed, the outside looked more crowded, the energy looked higher, and the structure looked layered. Piece by piece, the edge of the solar system was starting to look less like a calm frontier and more like a stressed contact zone. Did you expect the sun's shield to end in a clean line? Or does this sound more like a bent and battered border than a bubble? Tell me what you think, then like and subscribe, because the next part makes the whole picture even harder to trust. Many scientists also assumed that once Voyager 2 crossed the heliopause, particles from the sun would mostly stay behind. That would make sense if the heliosphere were a strong, well-sealed shield. Instead, Voyager 2 still detected a trickle of low-energy particles from the sun leaking beyond the boundary. The shield was not sealed shut. That single result is easy to miss, but it hits hard. A shield that leaks is a different kind of shield. Voyager 1 had not shown the same leak in the same way, which suggested that the heliosphere is not uniform all around. Voyager 2 crossed closer to the flank, the side region of the heliosphere, and that side may be more porous than the front. In plain language, our solar bubble may have weak spots. That does not mean cosmic rays are suddenly pouring into Earth tomorrow, but it does mean the frontier depends on direction, shape, and local conditions more than a simple round bubble model would imply. The shield protecting the planets may be strong in some regions and easier to penetrate in others. Then came another surprise that researchers had hoped would disappear with a second crossing. The magnetic field outside the heliopause lined up almost parallel with the field inside. Many scientists expected a sharper turn in direction once the spacecraft entered interstellar space. Instead, Voyager 2 confirmed the strange hint already seen by Voyager 1. That mattered because magnetic fields help shape how plasma moves and how particles cross boundaries. If the field outside continues in an oddly similar direction, then the border is not acting like two cleanly separate magnetic worlds touching each other. It suggests a more tangled relationship, one that is easier to describe as a blending zone than as a hard dividing line. So, look at the pattern. Scientists expected a boundary that moved clearly with the sun's cycle. Voyager 2 found a crossing distance oddly close to Voyager 1. Scientists expected cooler outside plasma. Voyager 2 found hotter plasma. Scientists expected a cleaner seal. Voyager 2 found leakage. Scientists expected a sharper magnetic change. Voyager 2 found strange alignment. One odd result can happen in any difficult mission. Two make people cautious. But when surprise piles on surprise, it stops looking like noise and starts looking like a message. That message is simple and deeply uncomfortable. The region that protects our solar system is more complex, more uneven, and more disturbed than many neat theories allowed. At this point, it is fair to ask what exactly makes that alarming. After all, Earth is still here. The sun still rises. Our skies do not look different because an old spacecraft found a hot, leaky boundary 11 billion miles away. The danger is not sudden panic. The danger is that we may not understand our own shield as well as we thought. And that matters because the heliosphere is not just a picture for textbooks. It is part of the environment that shapes how much deep space radiation reaches the inner planets. Radiation is one of the biggest long-term threats to spacecraft electronics and to human bodies on deep missions. If the shield is more porous or more stressed than expected, future exploration becomes harder to plan with confidence. Voyager 2 also showed that even after the crossing, it was not yet in fully calm, undisturbed interstellar space. Researchers describe the region beyond the heliopause as a perturbed transitional zone. That means the influence of the heliosphere seems to reach beyond the crossing itself. The sun's bubble leaves a wake, and the space just outside still carries signs of the struggle. That is a very strange idea to sit with. We like borders that say inside ends here and outside begins there. But the real border of the solar system seems to be messy, stretched, and active. You can cross it and still not be fully outside in the simple sense. That makes the solar system's frontier feel less like a doorway and more like surf at the edge of a stormy sea. There is another reason the re-examined data matters so much. Voyager 2 is old, and its best instruments cannot work forever. Its power comes from radioactive generators, and NASA says each Voyager loses about 4 watts of power every year. That may not sound serious on Earth, but out there, every watt matters. A slow power loss turns into hard choices. In 2024, NASA shut down Voyager 2's plasma science instrument to save power. That was the same instrument that had been critical in showing the craft cross the Heliopause in 2018. The mission still continues, and other instruments still work. NASA hopes Voyager 2 can keep returning some science into the 1930s, but only by cutting more systems as the years pass. That means the old data is becoming more precious, not less. Scientists cannot assume a better, fuller, endless stream of plasma readings will keep coming. Some of the most important clues may already be buried in the measurements Voyager 2 sent before that instrument went quiet. So when NASA and researchers re-examine deep space data, they are not doing a casual review. They are trying to read every line while the book is still open, and even reading that book is slow. Voyager 2 is so far away that commands take many hours to arrive, and the answer takes many more hours to come back. At the time of the Heliopause crossing, the one-way light time was about 19 hours. Today, it is even longer. No one is steering this craft in real time. That delay changes the feeling of the mission. Engineers on Earth send instructions and then wait almost 2 days to fully see the result. When something goes wrong, the silence stretches. When something goes right, the success arrives late. Voyager 2 is not just distant in space, it is distant in time, and things do go wrong. In 2019, NASA switched to a set of backup trajectory correction thrusters after the normal attitude thrusters began to degrade. Those thrusters help keep the antenna pointed at Earth. Without that pointing, the whisper from deep space would vanish. Keeping contact is a constant battle against age, distance, and shrinking power. More recently, NASA also had to deal with computer and data troubles on the aging craft. That matters because Voyager 2 is not a modern supercomputer. Its onboard computers process only about 8,000 instructions per second. For comparison, a modern phone can handle billions every second. Yet this old machine is still doing frontier science in a place nothing newer has reached. Does that make Voyager 2 feel more heroic to you, or more unsettling, like we are depending on our oldest scout to explain our most distant border? Leave your answer below, and if you love real space mysteries, subscribe so you do not miss the next one. Now let's get to the part many people overlook. A hot, dense, leaking boundary does not only tell us about the sun, it tells us something about the galaxy pressing back. The heliosphere exists because the solar wind pushes outward, but it also has a shape because interstellar space pushes inward. Voyager 2 suggests that outside pressure may matter more, or in stranger ways, than simple models once assumed. Imagine a ship moving through dark water. The front compresses what is ahead of it. The sides feel drag. The wake behind churns. NASA has used similar images to explain the heliosphere, and Voyager 2's data makes that picture feel less poetic and more literal. The sun is not floating in peace. It is plowing through an active medium. That could help explain why the plasma near the heliopause was hotter than expected. Compression heats particles. Shock waves can add energy. Turbulence can keep a region stirred. If the local interstellar medium around our solar system is rougher than we thought, then the heliosphere may be locked in a more violent pressure contest than old diagrams ever showed. Research tied to Voyager 1 has strengthened that idea. Scientists found signs of plasma waves and changing density in interstellar space, suggesting the region between stars is more like an ocean than a still vacuum. Solar eruptions can send shocks outward for years. When those shocks pass through sparse plasma, they can reveal structure that would otherwise stay hidden. The darkness out there is not dead calm. That makes Voyager 2's hotter outside readings harder to dismiss. If the very local interstellar medium is more energetic, then the pressure on the heliosphere changes. If the pressure changes, the shield's shape changes. If the shape changes, then the way cosmic rays enter changes too. One strange temperature reading can ripple outward into a whole new picture of our place in the galaxy. This is why scientists keep going back to the same measurements. They are not looking for a dramatic headline. They are trying to understand the basic physics of our home bubble. That includes how the sun interacts with the galaxy, how magnetic fields wrap and stretch, and how radiation is filtered before it reaches the planets. Those are not side questions. They are foundation questions. The Voyager 2 data also matters because we do not have many chances to test these ideas directly. Telescopes can infer a lot. Computer models can simulate a lot. But there is still nothing like having an instrument physically cross the boundary and report from both sides. That is why every inconsistency feels important. The sample is rare, and the witness is unique. And that witness is still moving. Voyager 2 travels at about 15.4 kilometers per second relative to the Sun.
That is fast on any human scale. Yet the emptiness is so vast that even at that speed it would take roughly 19,390 years to travel 1 light year. Deep space is so large that even a speeding spacecraft can spend a lifetime barely crossing the first inch of the map. That scale can hide the emotional side of the story, but it is there. Every year, Voyager 2 grows weaker. Every year, a little more power is gone. Every year, scientists know that one more instrument may have to be turned off, one more heater may go silent, one more link in the chain may fail. So when researchers reopen the old datasets and say the results are unsettling, they are speaking with urgency. This is not just another pile of numbers to sort whenever time allows. It is a narrowing window. We are learning about the edge of the solar system from a machine that cannot be replaced quickly, cannot be repaired, and cannot wait forever. That changes how every result feels. And maybe that is the most haunting part. Voyager 2 is revealing that our local shield may be hotter, more layered, more porous, and more magnetically strange than expected. But it is doing so in fragments, through an old body with failing power, speaking across almost impossible distance. The mystery is growing at the same time the witness is fading. Have you ever noticed how the scariest discoveries are not loud, but quiet, slow, and impossible to ignore once the pattern appears? If this story is getting under your skin, hit like, subscribe, and tell me which clue feels worst so far. Some people hear all this and ask a fair question. If the heliosphere is messy, why does that matter to ordinary life on Earth? The answer is that Earth lives deep inside a system shaped by these outer battles. We are not standing apart from the sun's bubble, we are passengers inside it. The heliosphere helps reduce part of the radiation coming from the wider galaxy.
That matters for technology, for astronauts, and for long future missions. It may even matter over huge stretches of time for how life experiences the cosmic environment around the solar system. So when Voyager 2 says the shield is not as simple as we thought, it is not reporting trivia. It is reporting on part of our shelter. This does not mean the shelter is failing tomorrow. We need to stay honest. The alarming part is not instant doom, it is uncertainty. A system we depend on appears harder to model and easier to misunderstand than expected. That kind of uncertainty matters, especially when planning the future beyond Earth. Think about humanity's next centuries, not just the next news cycle. We talk about bases on the Moon, long missions to Mars, advanced probes to the outer planets, and maybe one day missions that go farther than Voyager ever could. Radiation will be one of the biggest obstacles in all those dreams. Knowing how the sun's shield really works is part of solving that problem. Voyager 2 is forcing scientists to ask harder questions. How much does the local interstellar medium shape our bubble? How stable is the heliopause over time? Where are the weaker regions? How far beyond the crossing does the disturbed transition zone extend? And how much of our older picture was based on boundaries that were too clean to be real? Those questions are still open. That is another reason the results feel alarming. We are not looking at a mystery that has already been wrapped up. We are living in the middle of it. Voyager 2 is still out there, still moving deeper into interstellar space, still offering clues even as its resources shrink. And there is a poetic kind of fear in that. Humanity built this craft before most of the people alive today were born. It carries a golden record, a message from Earth meant for unknown listeners. Now, after all these decades, it has become a messenger in the other direction, telling us that the border around our own home is stranger than we imagined. That reversal is powerful. We sent Voyager 2 out to meet the universe. Now the universe is answering back through Voyager 2's instruments, and the answer is not comforting. It says our protective bubble has leaks. It says the outside is hotter. It says the line between here and there is not where we thought it was. And remember, this is not coming from hype. It is coming from years of careful reanalysis, cross-checks, instrument readings, and comparison with Voyager 1. That is what makes it so compelling. The results do not come from one flashy moment. They come from patient science, noticing that the same story keeps refusing to fit the old shape. It is also a reminder that exploration does not always make the world feel safer. Sometimes it does the opposite. Sometimes the farther we look, the more we realize that our home exists inside systems we barely understand. Voyager 2 has done that for the outer planets, and now it is doing it for the edge of the solar system itself. So the next time you hear someone say, "Space is empty," remember this old spacecraft crossing a hot, dense, leaking frontier. Remember that our star is blowing outward while the galaxy presses back. Remember that the shield around the planets is not just there, it is working, straining, and changing. And somewhere out in that dark, Voyager 2 keeps going. No applause reaches it, no headlines matter to it. It just drifts farther into the unknown, turning faint measurements into one of the most important warnings modern space science has received. Our corner of the cosmos is not as calm as it looks from the ground. What unsettles you most right now? That the boundary leaks? That the outside is hotter than expected? Or that we still do not fully understand the shield around our own solar system? Subscribe, turn on notifications, share this with someone who loves real science, and drop your answer in the comments because I really want to know. Thanks for watching, and I will see you in the next one.